so we're picking back up. So let's put you into snooze mode. So lecture 6, normalization, quick recap. We'll talk a little bit about keys, and then we'll move on to look at physical design of databases. A quick mention that tomorrow from 11 till 12, Moira will be available. She hasn't, again, sent an Eventbrite out this week because they didn't seem to have demand for it, but she'll be available from 11 till 12 in CSP1023, the small teaching space. You've got any issues with the previous 2 practicals? Or just generally with life? She's very good at general advice. Go and see Moira, but she'll be there if you need any help at all. And if you've got any questions, wave or try QChan. Hopefully the spam levels will be lower today, but who knows? Who knows? If you haven't done it, please do set up a MySQL account. Next week, your practical will be the stuff we're talking about this week. But next week, we start talking about SQL. So the week after, the practicals will be actually using MySQL. So if you haven't set up your account, set it up now. Set it up in the lab. If you've got any problems setting it up, bring those problems on Monday, and we'll have a look, or go and see Moira tomorrow in the session, so do it ASAP. So a quick recap, the normalization that we talked about on Tuesday. Most of you have heard of it in some way, shape, or form. A little bit of confusion. A few people seem to be, confused and angry, upset, angry about it. I get that quite a lot as a general reaction, but we've gone through it very quickly. We'll repeat it time and time again. If it doesn't click yet, if you're kind of like, what the hell, I don't understand it, just go through it. We'll take our time. You'll have plenty of time in the lab sessions in order to go through and have a look at it. So Wikipedia then, normalization had sort of these 2 very texty definitions, but the bits that I took out as key are reducing data redundancy and improving data integrity. And the 2 go hand in hand. If we have a lot of duplicate data in our system, then the chances of an integrity failure, i.e. that data getting out of sync, is going to be very, very high. So normalization is about creating rules and settings and that kind of thing that allows us to understand how the entities relate, create rules within our databases in order to do that, and we can be confident, if we do it properly and our database adheres to the rules that we create, that we are not in any danger of getting referential integrity problems within the system. So the process that we follow to go from unnormalized form to 3rd normal form, which is as far as we go, is laid out and worth repeating and practicing. So the first thing that we do is we split the attributes into whatever separate data units we can. We remove repeating groups into separate attributes. 2nd normal form, we split out our part key dependencies to tables that have a composite or combined key. Split out those entities that only rely on part of that, and then for 3rd normal form, go through and have a look and split out non-key dependencies, things that relate to stuff which are non-key specific. Now, there are different implementations of this, and database is one of these subjects that, although on the one hand, when we actually get to SQL and to looking at data, it's right or it's wrong. It's a bit like Java programming. You put code in, you run it, comes out the other end, and the output is either correct or it's not. The process of this kind of stuff, the design level, the normalization, there will almost certainly be different interpretations. So I can't remember who it was, but someone came down to see me at the end of the lecture on Tuesday, had a chat and was showing me one of the examples that we're going to look at in a minute, and they'd actually gone further than I had in terms of splitting it down. All right, so it may well be that you slightly end up with a slightly different answer. As long as you've roughly followed these processes and you've gone through, then all should be well. So we had a look at 2 practice examples to normalize to 3rd normal form. So this was the first one. Hopefully, we started that in the lecture. I think we left it with you, and you had a look at the first one, the second one. So this was the first one. Most of my examples are pet-related, just for fun. So this was a health history report for a pet, and we started with the ununified form, the unnormalized form at the bottom. We had a pet ID, pet name, pet type, pet age, owner, and then from repeating groups of the visit date, the procedure number, and the procedure name. So this was what you were first doing. So this was my solution to work through and do it. So again, let's just follow the process through. So the first thing we want to do is we want to remove the repeating groups, which are these things we've identified with brackets around them. So we're going to split the visits out. So we're going to end up with a separate entity for the visits, and we're going to split that away from the pet. So we obviously have a pet number as the unique identifier, so we've identified that, it's underlined. When we split the visit out, we need to give it some kind of key to identify it, and we also will need to link it somehow to the pet. So we usually create a foreign key, then linking back. So here, first normal form, we have a three-part composite key. We have the pet number, the visit date, and the procedure number. These uniquely identify the thing that we did to the dog on that day. If we didn't have all three parts of this key, we could do the same procedure to different pets on the same day if we just had these two. We could have the same pet visit a couple of times on these days, and we could have the same pet have the same procedure on different days. So in order to be sure, and this is, if you remember, when we started talking about keys, a combination of attributes that uniquely identify an instance of the entity, the pet, the day, the procedure. Now, you might turn around and you might say, actually, and this is where it comes down to an element of judgment, you might say, that's wrong. You might say, actually, what happens? Surely there must be a case where the very most unlucky dog in the world, has the same procedure on the same day. If that was the case, and what you had done there is instead you'd created a kind of visit ID or whatever, that would also be fine. That would be fine in terms of the answers that we came out with. So there we go. So unnormalized form, first normal form, split out the repeating group. So the second one then is part key dependencies. So are there any things in here? Obviously, they're not going to be here because there's only one key. Are there any things here that only depend on part of the key? Well, yes. The name of the procedure only depends on the procedure number. So we've split that out here. So procedure number now becomes a foreign key. Pet remains a foreign key. Here's our link entity in the middle, and procedure splits out and goes on. And then finally, are there any non-key dependencies within the system? Well, we can indeed identify some. We could say, okay, well, the owner, forename, and surname are not dependent on this necessarily, so we could split them out into a separate table. But again, this comes down to an element of you making a decision on what are reasonable ways of going about. But that was my example solution to the first exercise. Anyone have any particular questions on that? Anything that's unclear? Other than all of it? Okay, good. So let's move on. You can have a look at these. Oh, there's a hand up. Yes. You certainly could do. Yeah? So usually what would come out at this point is we're now going to start talking about the physical design, logical design of the database. So you certainly could do an ER diagram at that point, yeah. It would depend. Very rarely do we come across examples where something is completely unnormalized. So I give you these form examples. Usually you use an ER diagram at the start and possibly at the end. So you use an ER diagram here to try and understand what the entities, how they relate. Then you normalize and you'd update the ER diagram. It would depend on what you're doing, but certainly, yeah, you could do. Okay, so let's have a quick look. Oh, and then okay, so there's it written out in the kind of format that we like. Que sera, sera. So let's have a look then at the second example, another doggy-related one. It's invoices from work. So, so fairly obvious things, couple of assumptions. One clinic, price of procedure never changes. So an invoice for this person, and here are some repeating data. And this was then the kind of way I would work through and look at the solution. So we start off with our normalized form, invoice number, date, customer name, customer address, and then some details of the pet name, the procedure, and the amount. These are the repeating groups. Split the repeating groups out as the first step. So now we have the invoice and the pet being identified with the procedure and the amount. Split out part key dependencies coming here. So the pet name doesn't relate to the invoice. The pet name only relates to the pet number. So we split these out here. And then finally look through and try and identify things that don't rely on the keys. So in this case, we've got details of the customer here. So we can create a customer number, split that out. We have the pet there in the middle. Now, as I say, this is my workings of this. I've split the customer out. I've done it. Some people would go further, potentially, not quite as far. When we try and assess this work, when you do this, and you'll do some normalization, your course test in week 7, it's going to be, is it logical? That will be the challenge I give the markers. Is it logical? Is it reasonable? It won't be, does it exactly meet these same specifications? And then that would be our output, that we'd end up with the 5 entities, the invoice, the customer, the PET invoice specifically, the procedure, and the PET. All right? Yeah? I'm going to take that as a yes. I'm going to take that as a sort of like, for God's sake, move on. So you will get a chance, you get to practice this on Monday, because I know you want to. So you'll get to go through and have a good look at it on Monday. Normalization is one of these things that is awful. As I say, I think I gave you this speech. I probably did on Tuesday. I end up repeating myself a lot nowadays. When I did it, it was terrible. And when I had to come and design these notes to teach it, it was terrible. And I hate it, and it's awful. But I do it all the time. I do it in all of the systems that I build, in all the sort of consultancy work I do, and all the systems that we push out. The first thing I'm doing is I'm thinking, right, how do we remove duplication? How do we link things together? How do we do it? Understanding this process helps you academically. So understanding the steps, unnormalized form, first, second, third, you'll be required to demonstrate that for this. The learning outcome for this, and the thing that hopefully you will take with you, is the ethos and the reasoning behind it. All right. So anyway, those are the examples. Have a look at them. Make sure you're happy. Actually, I should rephrase that. Make sure you're not overly confused or miserable. I wouldn't say happy would be the right word with regard to this. And come along on Monday, and we'll go through some more examples on Monday. Well, you will, and we'll have a look. What we'll probably do, because this, as I say, is an area of some confusion, is we're going to move on next week. So next week, we're going to come in to look at SQL on the Tuesday, and we have the police coming on Thursday to talk about data in the real world and their real live systems, which should be a very interesting talk. The class tests, so this is what, week 4? Is this week 4? The class test isn't until week 7. Usually what we'll do is, coming up to that, I'll ask who wants to go back through stuff again. Last year, normalization was the most common topic, so we'll go back through it, and we'll have some opportunity for you to revisit it. Okay. Would we have to do first, second, third normal form in an exam, or just normalize? Yes, you would be expected to show the process from first, second to third normal form. Now, having said that, how the marks are usually structured in the kind of exams that I tend to do would be that there will be marks specifically for the correctness of the final answer, and then there will be separate marks for the process of you going through it. So if you're one of these people that don't believe in process, you just look at it, solve it, write that down, and just leave a note going, screw you, Dave, I'm not showing you my working, right? You will probably still get well above 40% in that question. Well above, you'll get somewhere in that region. If, however, you're someone that shows the process, and you show willing, but you go a bit crazy and lost towards the end, you'll still get good marks for showing it. If you show that you've applied the process correctly and got the correct end result, then you'll get full marks for that question. Okay. I see various things on here. We'll move on from this. If you've got any other questions or whatever, I'll try and have a look through QChan later and pick up any specifics and try and answer them. The second thing is, what we'll probably do is we'll see how you get on Monday with the practicals, and then I might do a few videos, explainer videos, kind of working through possible scenarios if that would be of use to people to look at outside. Okay, so keys. We looked at normalization. One of the things we do in normalization is we identify what are the keys. Keys uniquely identify an instance of an entity. We had the whole thing, what's your key? How does that work? How do we uniquely identify an instance of an entity? And primary keys are incredibly useful because they're unique. No two instances of an entity share the same individual instance of that key or combination of keys. So it allows us to uniquely identify that, absolutely. When we have our attribute diagram like this, if we want to add a simple key on, we just underline the item that's going to be the key. Or if we have a variety of fields which uniquely identify it, then we can have what we call a compound key. So a simple key is a single attribute that uniquely identifies it: national insurance number, student number, car registration number, whatever. And when we start with unnormalized, unsorted data, what we're usually doing is we're trying to come up with candidate keys. What are the possible things that either on their own or in combination can be used to uniquely identify as a primary key? If we can't find one thing, sometimes we invent it. So sometimes we'll say, okay, well, do you know what? To uniquely identify this data, we're going to give every record, we're going to give every instance an ID number. Other times we have to use a composite key, a combination of attributes that uniquely identifies what happens. So there, what we're trying to do is we're trying to find things that in combination, name, date of birth, address, uniquely identify an instance of that entity. So that's a quick recap of what we covered before. And again, we just underline them as we go on. Now we've started talking about normalization, we've started talking about splitting entities out and how they relate. We've also introduced the concept of a foreign key. So a foreign key, an attribute in one entity that uniquely identifies an instance of another. So we have an attribute within our record that is the primary key in another entity over here. I think it's for you. For example, we have a car. The car has a registration number, but it also has an owner. So in the car entity, we probably have an owner ID, which is the driving license number of a driver over here. So a foreign key is something within an entity. It doesn't identify that entity itself. It might be a composite key in order to do it, but it identifies uniquely another entity which is linked or is related to it. Whenever we're joining IDs and we're talking about entity relationships, we talk about one-to-many, that kind of thing. Whenever usually we have a one-to-many relationship, the side that has the one will have a reference in it. We'll have a foreign key in it to link it to the entity on the many side. And we identify these in most notation with an @ sign at the end. So here we have kind of, module code, blah, blah, blah. Lecturer code, location code. So lecturer code is going to uniquely identify the lecturer entity that's there. And location code uniquely identify the location that's there. So here we are storing in our first entity foreign keys, which in turn are primary keys in related entities, referencing other ones. This is all just part of the kind of way of understanding how relational databases work. The key thing with relational databases, the powerful thing, is that relation. So rather than relying on us to know that these are all related to each other, in a relational database, when we create it, we tell the database these are related to each other. We tell the database, hey, I want a table for a module. Oh, and by the way, here's another table for a lecturer and a location. And I want the references for these stored also in this one here. When we do that, we create it, we've normalized it, we've avoided duplication, right? And we also ensure that we have referential integrity. We ensure that you can't have a location code that doesn't actually exist. You can't have a lecturer code for a module that doesn't actually exist. And that's the purpose of this, to kind of put it all together. So we have these kind of things. So this is how foreign keys work. So that's a quick recap on keys. So we're now getting to the end of the design phase of the database. So this is what we were talking about, as we've gone through the weeks. We've talked about conceptual design, technical design, and now finally we're getting onto the physical design, which means, as I say, next week we're going to actually start looking at interacting with databases and writing code in order for it to work. So some of the terminology can be a little bit confusing. And this is very true when we start going from conceptual database talk, where we talk about entities and this kind of thing, to physical databases where we don't talk about entities, we talk about tables, we talk about rows, we talk about columns, we talk about the actual things that are contained and written to the disk. Because don't get me wrong, all of the design stuff that we've covered is hugely important. But you can be as airy-fairy as you like, and you can come up with these brilliant ideas of relational entity mapping and blah, 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 blah. Someone has to actually write SQL to create it in a database, because otherwise, what's the use? It's not actually applied, it's not practical, it's of no use to anyone out there. So generally, when we talk about these things, well, entity is a table in a database. An attribute is a field or a column, depending on your phraseology. And an instance of an entity is a row within that table. So if you think about an Excel spreadsheet, for an example, and obviously this is a very bad example of a relational database, but if I said to you, OK, I want you to store a list of students in Excel, right? So the first thing is that the table will be our sheet. So we have a file, student.xx. Within that, we will have, I don't know, ID, name, phone number. These are the attributes that we're talking about. These are the things that we store data about. They are the columns. And then each individual student, you, and you, and you, and you, instances of students will be rows within that table. So that's it. That's the why. When we talk about these things, we're moving over. That the attributes become columns. If we look at things in tabular view, the attributes are fields within the database that we're going to be able to query. The tables are the entities, the collections of data about a specific entity. And each row within our entity table is an instance of that entity, a list of data that we're going to go on. And this format, this way of seeing it, is very useful, and it's how we interact with most databases. When I move on and we'll look at actually using databases and doing that kind of thing, you'll often as not see it presented as this kind of table, looking very much like it was Microsoft Excel or whatever. How it does it inside itself, how it stores the files, how it organizes things, well, that's up to the database engine. But how we see things is, here are the columns, the attributes, and here are the instances, the rows across it. So that's the kind of terminology to get around. So we're going to talk a little bit now about physical constraints and physical types of data. So the first thing is that when we're working in the normal world, and we're working in the sort of conceptual thing, we can really call attributes, tables, entities, you know, anything we want. And sometimes they have really long names. Date of birth of human shell hosting lizard king. Call it whatever you want. Name of student who has appeared in disciplinary for trouser malfunction in cafe. You know, whatever you want to call it. But usually when we implement our database, there may well be constraints on the names. Less often now, but some databases still have it. There's going to be a length constraint. We can't just call things a million things. And the second thing is that it might be that we want to use some kind of notation to indicate what things are. And database purists, in fact, a lot of programming purists, have this thing where everything that has a name should start with a description. So every table, you shouldn't call it dinner, you call it TBL dinner. So we know it's definitely a table. This kind of thing. But there may well be constraints. And certainly spaces are often a huge problem. So we need to remove those, replace them with underscores. We might also have reserved words, words that we can't use, words that blow up the system as it happens. So we have our tables, and we know our fields, we know the attributes that we're going to map to it. But in order to actually turn this into an actual database, we need to know a bunch of other stuff about it. And the first thing really we want to decide is what's the data type of the field? What are the constraints potentially upon that? And as with Java, as with programming, there are different types of data. The different types of data determines things like how they're stored, how they're searched, and obviously what we can store in them. And it's very important to try and get the right type of data type identified. We have to get the right one selected early on, or else we can't store the data correctly. So let's just have a quick think about what are the types of data that you expect to see. Could be Java, yeah, similar to Java. What data types are we talking about? You can shout out. Come on, it's late. A date, yes. Very good. Any other types of date? So a date is a year, month, day. Date, time. What about just a time? 3 o'clock. So yeah, okay, so date and time, temporal information, right? Useful in the TARDIS for skipping around. Brilliant, very good. Any more? Sorry? An int, yes. So numeric data, and it's specifically integer. What other types of numeric data might we want to store? Double, yeah. So some kind of floating point number of various precision. Do we only ever have one type of int? Anyone heard of a long? Unsigned? Okay. So, okay, numeric, int, double, temporal. Anything else? Boolean, yes. That's what we like. We like Boolean because things are either right or wrong, right? We don't like anything else. Any more for any more? String, yeah, text. Okay, some kind of text field in order to go in. So there are, even thinking about it, there's a whole bunch of potential ones that we can do. Now, you'd like to think, okay, int's an int, date's a date, everything's fine. Nothing's simple in databases because different RDBMSs, different relational database management systems have very different ways of storing and relating data. This can cause problems between it, but for most data types nowadays, there's usually quite a degree of overlap. And we are going to be looking at MySQL. So all we're going to look at, all we're going to concentrate on, all we need to know is the MySQL data type notations and what goes in. Quite a lot of MySQL data types we not only can give a type to, but we can give a length to as well. And the length is going to determine how much data is going to be reserved for us. So when we say, OK, I want a string, here's how long I want it to potentially be. How much space on the disk, how much space in memory, if it's a memory table, whatever, needs to go out. So the idea is we have a type, and then possibly we have a length as well in order to look at. So let's have a look at some of the MySQL data types. So let's start numeric. So we have tinyInt. It's a very small integer. So it's either -128 to 127, it's signed, or it's 0 to 255 unsigned. Someone smart, tell me why that is. Why that range? Sorry? Yeah, okay, so we can go that. Why is the range only 255, whether it's signed or unsigned? 8-bit, yeah, absolutely. So this harks back to the good old days of computing, when I used to understand computers, right? 8-bit computing. I don't know why we needed more bits. So yeah, tinyInt is an 8-bit number, and in a Word, a modern 32-bit system using words, these will still be represented in 8-bit segments. So tinyInt. We then have smallInt, mediumInt, and just int, of course. We also have bigInt. So all of these different ints. And theoretically, that can go from minus, I'm not going to read it out, to plus, some ridiculous range of numbers. So I mean, that's what, 3, 6, 9, 2, I don't know, 22 exponents, something like that. So some ridiculous range of numbers. That's the theoretical maximum, but it then depends on the operating system, because MySQL might be, up to record it, but if you're trying to run it on a 32-bit operating system or whatever, then you're probably going to have issues actually getting that range in. So we have the idea of integers, lots of different types of integer. Float, floating point number, someone mentioned. We have float and double, just like we do in Java. More precise, large double numbers. And then Boolean. Yes, no. And Boolean is actually synonymous for tinyInt1. So it's 1 bit of data. It can represent a 0 or a 1, decimal value 0 or 1, or a Boolean. Yes or no. So more date. exactly right, day precision. Date time, a date and time in combination, a specific date, a specific time. Time stamp, another way to store date and time. So date time has microsecond precision, timestamp millisecond precision. Just time. Just the year. Now, you might think, looking at this, why? Why did someone sit and they were like, oh, yes, we need a date and we need a year type, right? It's because these people try and be as flexible as possible. And if we were dealing at PETA scale, if we are Facebook or whatever, then the ability to just decompose, so rather than saying, look, we'll store it in a date and we'll call everything January the 1st. We only need the year, but we'll say January the 1st and we'll reuse the same type. That waste of 0101 as decimals, so sort of 64 bits potentially, is significantly wasteful when you scale it up massively. It's also a lot more complicated to search it. Because if I'm only interested in 1970, and I have to say, oh, it's a date time, but I'm interested in any date from the 1st of the 1st, 1970 to the 31st of the 12th, 1970, that becomes a much more complicated search space and a much more complicated problem in order to do. So therefore, we always try and store the simplest type that we need in order to do it. So some more data types. Char, a fixed length set of characters. Varchar, a variable length of characters. So again, early on, there's an issue. If I say I want to store characters, right, and I want to store a name in character space, I need to really be able to cope with the longest possible name that someone is going to give. Okay, how long do you think the longest name is in this room, do we reckon? Who's got the longest name? Does anyone, any candidates for the longest name want to tell us their name? You know, we might say, okay, look, maybe 128 characters with all the middle names, maybe 256, maybe 512. But for most people, the name is going to be significantly shorter than this potential maximum. So then we get another thing. We say, okay, well, we don't want to ever say to someone, sorry, your name is too ridiculously long. You cannot use our data system. But we don't want to store loads and loads and loads and loads and loads of empty space. We don't want to reserve every time 512 characters long, and most people go, Joe Smith. It's incredibly wasteful. So we have the two concepts here. We have char. Char is a fixed amount. Char 32 is 32 bytes. It's always 32 bytes. It reserves 32 bytes on the hard drive, and whether you want it or not, it will use 32 bytes. You try and store 33 in it, it will blow up. You store 30 in it, or less than 32, and it wastes space. Varchar, variable char, says, I'll need up to. So when we're not sure, when we're going to have a high degree of entropy within our range, when we're dealing with things like name, where we're going to have two people that have really, really long names, we're going to have two people that have really short names, and everyone else is going to be somewhere in the middle, we use a varchar. Varchar requires more CPU power because to search it and to use it, we're not using fixed width, but it's much more efficient in terms of storage. So you can see that if we try and store with comparing a char here with a varchar, if we're storing nothing with a char 4, we use 4 bytes. We store ABC, we use 4 bytes. We store ABCD, we use 4 bytes. But when we use a varchar, we're only ever going to use the length we need plus 1. So if we're always doing short strings, sure, varchar uses more and it has more cost and it has more use. But if we say I want a varchar of length 128 and we store ABCD, we're still only going to use 5 bytes in order to do it. So variable char. Varchar is usually, unless you can be confident of the length being at the higher end of the range, varchar is normally what we do. We also have a text type, which is larger text storage. So your deep and interesting blog posts about how much you like cats can go on there. And of course, we have text, tiny text, text, medium text, and long text, depending on what we have to do. We support enumeration. So we may well have a data type where we want to specify it's one of a specific type. You've done enumerators in Java yet? Yeah? Oh, thank God. OK, that's good, right? So we won't go down that road. So enumerators to represent a specific set of discrete values. So there's loads. There's loads and loads of different data types that we can put on. And the trick is always to find what's the right type for the right field. So if you looked at something like this, right data types, we might say what's going on. I'll give you a second just to have a look and make your own minds up. So let's have a look. So I would say for a phone number, probably a char. Char 11, char 16. Not a number. We don't normally store phone numbers as numbers because we'll lose leading zeros. We might also have things like plus-in and country codes. A lot of countries, a lot of US codes have dashes in, or apparently do. So we probably record it now. Phone numbers usually tend to be around the same length, unlike names. If we said, OK, even international numbers, so a full UK number with STD code is 11 digits, an international number might be up to sort of 12, 14, 16, something like that. So we could pretty much do it. But every phone number that goes in is going to be somewhere in that range. We could go char on that. If we wanted to deal with the potential that there would be very long numbers, very short numbers, we could consider varchar. Name, I would certainly always consider varchar for the reasons I've talked about. We decided a maximum length. For many years, MySQL had a maximum varchar length of about 255 characters. That's not true anymore, so you might as well make it a lot longer, but you probably want to put an upper bound on. Date of birth is a date. I don't know the time that you were born. I only know the date, so we'd have that as a date pretty obviously. Password is going to be some kind of varchar, because some people's password might be shorter, might be longer. Although we probably will hash it. If any of you are aware of hashing mechanisms like SHA-1, all the other SHAs, they output hashed values which are of a fixed length, no matter how long the password is. So maybe then we'd use a char in order to keep it. Email, probably a varchar. Blog post is going to be very long. It's going to be longer than most varchars. We tend to use a text field there because it could be essay length. And finally, a login retry limit is probably going to be an integer at the other end. So we considered then, here's our attributes in our entity, in our table. What are the types going to be? The next thing to think about is what other additional details is there on this attribute that we would need to do? So the first thing is, is it required, yes or no? Can it be null? Can we create an instance of the entity that doesn't have this detail recorded to it? Is it indexed for speed? Now, we come back and we talk about indexes later on, but generally, if we're searching on a field, we index it. It means that we use more disk space, but it's quicker to find it. Is there a default value? If I create a record and I don't provide a value for this, is there a default? You wouldn't think we'd have a default name, but we might have a default access level. We might have a default systems administration key or a default password. Must the entity be unique? Must that attribute in that list of entities be unique? Must there be no other duplicates within it? We take all of this stuff and we put this into a thing called the data dictionary. And the data dictionary is a formal definition. It's a document that defines what are the fields, what are the types, are they required, are they not, are they unique, etc., etc. It becomes, hopefully, a living document. What you should do is when you make changes to the database, you should update the data dictionary, hopefully. Often you'll find people don't, and then you end up horribly undocumented as you go along. There are lots of different formats. This is one. This is the one that we tend to use here in order to go on. And you can see, pretty simply, there's some description at the bottom, details of what it's related to, the tables, any description on the table, field names, the attributes, required, indexed, unique, type, length, any rules, any default value, description, and example of the typical data that needs to go into it. So the idea is this is a textual document that allows you to explain how you're actually going to implement the database. I've had our design, I've had our entities, we've identified our attributes. This is what the tables are going to look like, and this is what the rules are going to go out. And this is what you'll be enjoying on Monday. So there we are. We have covered database design in 3-ish weeks. Sure, it felt like longer. We started with the logical, or sorry, the conceptual, the essence of it. What are the ideas? What are the entities? What are the conceptual, philosophical relationships? We've moved on to the logical. What are the attributes? What do they have? How are they related? What do they do? And then finally, we come on to the physical. What's that going to look like in a database? What are the fields going to be? What type are we going to use? How are we going to store them? Are we going to index them? How are we going to ensure referential integrity? Please remember, if you haven't set up a MySQL hosted account, please do so ASAP. Do it on Monday. There is the summary of what we've got on. I think that was pretty much it. Normalization and physical design on Monday. I know you love it. You'll look forward to it. And I will go through QChan and see if there's any questions on there.